Have you ever stopped to think about what actually happens when you tap Run in Android Studio? You write Kotlin, beautiful, expressive Kotlin with data classes and coroutines and extension functions. But here is the thing, your CPU has absolutely no idea what Kotlin is. It does not speak Java. It does not speak any human language at all. Your processor only understands numbers, tiny electrical signals representing ones and zeros. So how does the text you type become something a chip can execute? That is what this video is about. And I think once you see the full picture, you will never look at your code the same way again. Let us set the stage. You open a file, you type val x equals 5 plus 3, and you expect the number 8 to appear somewhere. Simple, right? But think about what needs to happen for that to work. You typed characters, letters, symbols, spaces. Your CPU does not process characters. It processes voltages on microscopic wires. Between you and the machine, there is an enormous gap, and bridging that gap is not one step. It is a whole chain of translations, each one bringing your intent closer to something the hardware can physically perform. Let us walk through that chain, starting from the top. When you write Kotlin and hit build, the first thing that happens is compilation. The Kotlin compiler reads your source code, which is just a text file, parses it, checks that everything makes sense, and then translates it into something called bytecode. Now, if you are an Android developer, you have probably heard of bytecode, but what is it really? Think of it like a universal instruction manual. Your Kotlin source code is specific to Kotlin, but bytecode is a lower-level set of instructions designed for a virtual machine to understand. On Android, that virtual machine is RTI, the Android runtime. On desktop Java, it is the JVM. The key idea is that bytecode is not machine code yet. It is an intermediate step. It is closer to what the CPU needs, but it is not the final destination. You can actually look at this bytecode yourself. In Android Studio, go to Tools, then Kotlin, then Show Kotlin bytecode. You will see instructions like eloadd, eadd, eStore. They look cryptic, but they are simple operations. Load a number, add two numbers, store the result. So eventually, those bytecode instructions need to become real machine instructions that the CPU can execute. And what the CPU does is shockingly simple. It runs a loop. Fetch, decode, execute. That is it. Over and over, billions of times per second. Fetch means go grab the next instruction from memory. Decode means figure out what that instruction is asking. Fetch means go grab the next instruction from memory. Decode means figure get that. Execute means actually do it. Then move on to the next one, your entire phone. Every app, every animation, every network call is powered by this tiny three-step loop running at incredible speed. There is nothing magical inside the chip. It is just this cycle, repeated relentlessly. Now let us zoom in on what is inside the CPU that makes the execute step work. There are two key pieces I want you to know about. First, registers. These are tiny storage slots built right into the processor. Think of them like a handful of sticky notes on your desk. You can scribble a number on one, glance at it instantly, and use it in your next calculation. Registers are the fastest memory your computer has, way faster than RAM, incomparably faster than disk. But there are very few of them, typically 16 to 32 on a modern processor. Second, the ALU, the arithmetic logic unit. This is the part that actually does math and logic. When the CPU decodes an instruction that says add these two numbers, it sends the values from two registers into the ALU. The ALU produces the result, and that result gets stored back into a register. So when you write val x x5 plus 3, what eventually happens at the hardware level is something like load the number 5 into register 1, load the number 3 into register 2, tell the ALU to add them, and store the result. 8 into register 3. That is it. That is what addition looks like to your phone. Let me show you the full chain so you can see how it connects. You start with Kotlin source code. The Kotlin compiler turns that into JVM bytecode. those ILOWED and IAD instructions. On Android, a tool called D8 converts that JVM bytecode into DEX bytecode, which is the format RART understands. Then at runtime, ART interprets or compiles the DEX bytecode into native machine instructions, the actual ones and zeros your ARM processor fetches, decodes, and executes. So the chain is Kotlin to JVM bytecode, to DEX bytecode, to machine code, to electrical signals. 5 layers of translation between what you type and what physically happens. Every single line of Kotlin you have ever written goes through this pipeline. It is happening right now on your phone, thousands of times a second. Here is where it gets really interesting. Early Android, the Dalvik days, used to interpret bytecode at runtime, translating each instruction one at a time as it came up. This worked, but it was slow. Modern art is much smarter. It uses something called JIT compilation, just-in-time compilation. The idea is simple and brilliant. Arty starts by interpreting your bytecode normally, but it is also watching. It notices which methods get called over and over, your recycler view adapters on-bind view holder, your network parsing logic, your tight loops. When it spots a hot method, one that runs frequently, it compiles that specific method into optimized native machine code on the fly. Now, instead of translating bytecode every time that method runs, the CPU executes native instructions directly, no middleman. This is why your app might feel slightly sluggish when it first launches, but gets faster the longer it runs. ART is learning your app's patterns and optimizing in real time. Art actually has a second trick as well. It is called AOT compilation. Ahead of time, when your phone is idle and charging, RT looks at profiles of how your app has been used and precompiles the hottest methods into native code. So the next time you launch the app, those methods are already optimized. No warm-up needed. This is the best of both worlds. JIT handles the immediate runtime optimization. AOT handles long-term optimization based on real usage patterns. Together, they mean your Kotlin code is not running as interpreted bytecode most of the time. The parts that matter most are running as finely tuned machine instructions, almost as if you had written them in C-Daishin. Now I want to step back and share something that I think is genuinely mind-bending. When you look at your Kotlin code and you think about it running, you probably imagine the computer somehow understanding your logic, following your if statements, evaluating your expressions. But that is an illusion, a beautiful, useful illusion, but an illusion. What is actually happening is numbers being moved between tiny storage slots. The CPU does not know what a string is. It does not know what a list is. It has never heard of a view model. All it knows is grab this number, put it there, add these two, compare that one to 0, jump to a different instruction if the result was true. Every abstraction you work with, objects, classes, functions, coroutines, eventually dissolves into these primitive operations. The computer is not running your code. It is running numbers. Your code is just a human-friendly description of which numbers to move where. So why should you, an Android developer, care about any of this? 3 reasons. First, debugging. When you see a stack trace or step through code in a debugger, you are seeing an approximation. The debugger maps machine-level state back to your source code, but sometimes, especially with optimized code, things do not line up perfectly. Understanding the layers of translation helps you make sense of those moments. Second, performance. When someone says avoid allocations in tight loops or inline functions reduce call overhead, those statements only make sense when you understand what is happening underneath. An allocation means asking the runtime to find and reserve memory. A function call means pushing values onto a stack, jumping to a new instruction address and jumping back. These are real CPU operations with real costs. Third, tools. The profiler, the memory inspector, the layout inspector, all of these tools are showing you a translated view of what the machine is doing. The better you understand the machine, the better you can interpret what these tools are telling you. Let us recap the journey. You write Kotlin human-readable text. The compiler turns it into bytecode, a platform-independent intermediate language. On Android, that becomes DEX bytecode for the ART runtime. RT interprets it, then JET compiles the hot paths into native machine code. The CPU fetches each instruction, decodes it, and executes it using registers and an ALU, billions of times per second. And the whole thing, every app, every feature, every animation, is just numbers being shuffled through silicon at extraordinary speed. In the next video, we are going to zoom in on what happens when your code needs to remember things, how memory actually works, from registers to RAM to disk. Because where your data lives changes everything about how fast your code runs. See you there.